So first of all, welcome everyone. Today, Matthew Browning will be talking about an observational introduction to stellar rotation and magnetism. And this is the first talk in the series of lectures associated with the Kavli summer program. Matt did his PhD at the University of Colorado with Yuri Tumre. He held postdoc positions at UC Berkeley and at the same time University of Chicago. And then he was at the Canadian Institute for Theoretical Astrophysics in Toronto, right? And he was awarded the ERC Starting Grant in 2013 for convective heat transport and stellar magnetism. And he is now an associate professor at the University of Exeter. And he works on stellar convection, magnetism, and the simulation of astrophysical fluids. And that's what I wanted to say. Take it away, Matt.
Thanks, Aaron. I'll get my screen set up here. Thanks for the invitation to come and speak to you guys. Wish we could be doing it in person, but this will work for now. It's great to see some familiar faces and some new ones too. So, right. This school is about the fluid dynamics of the sun and stars, and the subset of that topic that I'll be talking about over these 3 lectures really is rotation and convection and magnetism, and how those things are kind of interlinked, how they affect one another, how you can observe them, and how you can learn about them through theory and simulation and all the rest of it. In other words, what we're really aiming towards is, how do you get something like that? I'm pointing at this image in the bottom left is the sun. We'll talk about the other ones as we go along. But and I guess these lectures in particular are kind of a prelude, if you like, to the more sophisticated and more specific technical talks that you'll be hearing throughout the week and in the weeks to come. And I guess as I was writing them, I had 2 audiences in mind. One is really somebody who's coming from, let's say, plasma physics or fluid dynamics and knows that subject okay, but hasn't maybe looked too much at stars in particular, doesn't have a sense of what stars can do for plasma physics. And so for that person, I wanted to give a sense of, what are some of the interesting puzzles that are out there, what can we observe and how do we observe it, because that kind of colors the questions you can answer, and just a general sense of what can stars do for you? What is it that observations of stellar magnetism, stellar rotation, stellar convection, what can those tell you that is difficult or impossible to learn from an experiment in a lab? And then the other audience I had in mind is really somebody who knows stellar astronomy, but is maybe less familiar with the interior. Maybe they've taken one course in fluid dynamics, but they haven't taken magnetohydrodynamics, or haven't studied the interiors of stars specifically. And so I wanted to give a sense of some of the tools that we use as we talk about those things. And just broadly speaking, this first lecture is aimed at that first audience. So that is the person who doesn't know that much about stellar astronomy. So this is kind of stellar observational convection, rotation, and magnetism 101. The second lecture will be aimed more squarely at somebody who is new to MHD. So I wanted just to give you a sense of a kind of intuitive feel for the different processes that play out in stellar interiors and how convection and rotation and magnetism might interact in different ways. And then in the third lecture, I'll be a little bit more specific and talk about some specific problems in convection and magnetism, and really trying to get at this question of how do you build an ordered magnetic field like the one that we see in the sun and in other stars. Right. So before we get into all that, I wanted to talk a little bit about just why you might care about any of this stuff, and why I in particular care about any of it. And one reason you might care is that we live next to a star that has some magnetism. So the sun has magnetism over every scale you can imagine. Maybe the most famous example are active regions or sunspots, these dark blemishes on the surface of the sun. But if you zoom in, this is going to show some white light images, and then a rendering of chromospheric emission, and then finally a magnetogram. There's magnetism on every scale you can observe. and while there's a great deal of kind of small-scale magnetic noise, chaff, some people like to call it, and there's also this more ordered field on the very largest scales present in the system. So one example of that are these active regions. So you're seeing these pairs of oppositely directed polarities. One polarity is rendered as white in this plot, and one is dark. So you're seeing a magnetic field that's kind of poking out from the surface, and the sense of all these pairs, which polarity leads and which one trails, is largely the same for most spots in one hemisphere of the sun, and it's pretty much the opposite for most spots, most active region pairs in the southern hemisphere. So that's telling you something about the global organization of the field. It's telling you that the field that you see in active regions, and to a certain extent the field you see in other tracers of the field, is globally organized. It knows something about which hemisphere it's in, for example. And the overall polarity of the field flips every roughly 11 years. Lots of examples of this. Probably the most famous is this so-called butterfly diagram on the top. This is just showing the area occupied by sunspots as a function of time and latitude. So spots tend to appear first at mid-latitudes and then progressively nearer and near the equator over the course of roughly an 11-year cycle. And because of that overall polarity flip, then we say that the cycle is 22 years. So in other words, there is some order to this thing, and that is hard to understand when you first see it. It ought to kind of knock your socks off, because if you figured out any of the numbers that fluid dynamicists like to use, if we talk about anything over a diffusivity, so the induction relative to the diffusivity, buoyancy driving over diffusivity, the inertia over so the Reynolds or Rayleigh or magnetic Reynolds numbers, all those numbers are just enormous, right? In other words, just about any effect you can think of is big compared to diffusivity, and because of that, the solar convection, we think, is a very, very turbulent place. And amidst that turbulence, amidst that kind of chaos, there's still somehow this ordered field that gets built. It's not just a tangled mess, it has this kind of coherence to it. And so that's a real challenge to theory. So that is one kind of interesting bit of motivation for my lectures, and for, I think probably most of the lectures we'll talk about, most of the talks we'll see at this school. And you can learn a lot from just the sun. One annoying thing is that you can't, it's kind of one experiment. You can't go and change the rotation rate on the sun. You can't change its luminosity. And so that, to do that, to learn how these physical processes are affected by things like the rotation rate or the luminosity or what have you, we go and look at other kinds of stars. And the thread that runs through that observation, I would say, is just this tremendous diversity of outcomes. So if you go and look at the rotation and magnetism and convection of other stars, you tend to find that some have these whoppingly strong magnetic fields. We'll talk more about some of this later, but this panel on the left is a so-called Zeeman Doppler imaging, a spectropolarimetric measurement of the field in a particular low-mass, fully convective star. This whopping coherent field of sort of global Kilgauss strength. So some sort of stars have really strong magnetic fields, others don't. If you look at the fraction of stars that show magnetic activity in a particular tracer, let's say, which we'll talk about again in a minute, as a function of spectral type, some seem to be really active and others aren't. Others you can't see any trace of magnetism at all. So why is that? And if you monitor these things over time, as you go looking for the signs of surface magnetic activity over periods of years or decades, some seem to have very clear cyclical patterns to their activity, akin at some level to what we see in the sun, and others don't. So that's also a mystery. We'd like to understand how those things, those are kind of observational clues that spectral type matters and rotation matters and all the rest of it matters. So that's the kind of story that we're going to be getting at today. And then taking even a step back, you'd like to understand how any of that stuff, if you weren't interested at all in stellar magnetism for its own sake, just a hard-nosed stellar astronomer, and you want to know how it's going to affect stellar evolution or stellar structure or whatever, you'd like to know, is there an effect? Does rotation or magnetism or convection, the details of convection, I should say, does that matter for the life of a star? And if so, how? So that's the kind of story of these lectures, I guess. So before we talk too much about what you actually see, I thought I should say for a minute, because we have this range of backgrounds, just a little bit about how you measure this stuff, because that colors, again, the things that you can ask, the questions you can ask. It influences what we can what it even makes sense to talk about from an astronomical point of view. It doesn't mean the physical questions are less interesting, but if you want to interest astronomers in it, it has to be measurable. So astronomy 101, we measure photons. What we get are photons, right? And the photons come in from your favorite star. They hit your detector, and you can measure them as a function, of count how many come in as a function of, say, wavelength. In other words, you measure a spectrum. You could measure how many come in as a function of time. So you do photometry, for example, with some time series. You could maybe measure where, as a function of position on the sky, these things happen. And maybe you know some things about polarization states. That's pretty much it, right? Unless you have a gravitational wave detector or something. And as you get better and better measurements along each of these axes, you learn new stuff, okay? And a lot of the advances, I would say, in stellar rotation and convection and magnetism, all this stuff, are driven by improvements along one or more of these axes. And of course, you can combine them too. Just to pick an example, you could measure, say you wanted to measure magnetic fields or rotation. So you could look, for example, at the Zeeman broadening. There's a Zeeman broadening, a Zeeman effect associated with the presence of a strong magnetic field. So you could look, if you have precision along that wavelength axis, you might look for the Zeeman broadening or Zeeman splitting, if you have polarization information, of spectral lines induced by the magnetic field, and you get some information that way. Alternatively, if you had information in the time domain, a magnetic field, a big dark spot transiting across the surface, you might expect will lead to some photometric signature. So you could look at that as a function of time and learn some things in that way about the activity at the stellar surface in a sample of different stars. This is just looking at that photometric variation with Kepler and a series of periodic G dwarfs and M dwarfs. And so that's, again, along the time domain. In an extreme case, you might hope to be able to get very, very precise information on the sky. So information about the brightness, intensity as a function of position. One really beautiful example of that is some of this interferometric results. This is from Rottenbacher, 2016. In a few limited cases, this is a very large star that happens to be very close to us. You can actually image the stellar surface with interferometry and see where you have dark patches, which maybe correspond to magnetic fields in some way. And just so you can learn a lot basically from these different things, and as we get better and better along each of these axes, we can learn more and more things about stellar rotation and magnetism. But the links are not always so clear. It's sometimes a little bit more complex than you might think. So to pick one example of that, suppose we were looking at photometric variability. We want to know, you might expect that, gee, look, we see sunspots on the surface of a star like the sun. And if I looked at the photometric signature of that as a function of time, you might expect that I'd see less flux, it's a dark spot. And so the star would be dimmer when there are lots of spots on the surface. For a star like the sun, that's not the case. It turns out that the sun's actually brighter at solar maximum, essentially because the faculae, so these bright points elsewhere on the sun, dominate over the relatively small dimming associated with spots. That may be different in stars that are covered by much larger scale activations. But the point is just that the links between this stuff are not always quite so clear. Similarly, with the magnetic field, it's useful to think for a second about what kinds of fields you can measure and what you're missing when you try to do those measurements. So I picked just one example of this, which has to do with this Zeeman effect associated with the presence of a strong magnetic field. Very crudely, you can think about two different effects. One is that if you have a magnetic field, you can actually shift to the energy levels themselves. Okay, so that's one effect. And that depends, the atom doesn't know which direction you're looking at it from. So the energy splitting depends on the total field, the field energy, or what people call the unsigned flux, so the total field strength that is there. Alternatively, there are signatures, particularly if you imagine a photon propagating out, there are signatures in the polarized light, and that's a kind of separate thing. But roughly speaking, and this is from a nice review by Ansgar Reiners from a few years ago, looking at observations of pulsar magnetic fields, which I recommend to you if you're interested in this stuff. broadly speaking, if you're looking at integrated light, so what's called Stokes' eye, you're looking at the Zeeman broadening or spectral line, the presence of a kind of kilogauss strength, the signal associated with a kilogauss strength field is equivalent to something like a velocity broadening of about 1 kilometer a second. So a kilogauss field is pretty strong. And to understand what that means, to understand what 1 kilometer a second means, you kind of need to think a little bit about, and I'm not going to do this for you here, but it's an exercise for the students, I feel like. A typical good spectrograph today might have a resolving power of something like 60 to 100,000. And what that means is that the figure of merit here is delta lambda that you're able to distinguish over lambda. And roughly speaking, the Doppler shift associated with a certain velocity is v over c. So you can work out what kinds of velocities that R of 60,000 spectrograph is sensitive to. Roughly, if you have something that's 50 to 100,000, the smallest Doppler shifts you can measure are of order a couple kilometers a second. That's sort of the scale of things. So if you go and look at that has a bunch of implications for you as you go out and try to measure rotation and magnetic activity on a real star. So in particular, if it's very, very difficult to measure by information in the spectral domain in this way. It's very, very hard to measure rotational broadening that is of order the sun's rotation, right? You need something to be spinning quite a bit more rapidly than that to be able to see the rotational broadening. So many stars are essentially, their rotation is essentially invisible to us by this measure. Now, if you look at photometric rotation periods, you can monitor, if you're lucky enough to have a star that has some magnetic activity, and you can monitor the photometric activity over a long period of time, you can see, maybe you could pluck out the rotation period that way. Trouble there is that, as we'll see in a second, the rotation and the activity are sort of linked. And so the stars that tend to be rotating very slowly tend also not to be particularly active. And so it's quite hard to measure some of these things. And magnetic fields typically, and so when I say that the presence of a kilogauss field is associated with a roughly 1 kilometer a second signal, that is not easy to measure. So it's in integrated light, in Stokes' eye, it's difficult to measure fields that are less than a kilogauss or so. You can combine information from some of these different channels, and a lot of the most interesting observational constraints nowadays are coming from those kinds of combinations. So for example, if you wanted to look at the signature, you have some cool spot on the surface of a star, it might have a signature in the temperature field, a brightness field. You could look at that with by monitoring it both as a function of time and it in spectral lines. You can infer some things both about the darkness on the surface, but also the magnetic field strength. So this is basically giving you a one-slide overview of something called spectropolarimetry. You can look up papers by Oleg Kochikov to find out lots more about that. The hand wavily, you can say that, again, there's these two effects. One, it has to do with the overall field energy or the unsigned flux. And then there's another which has to do with the line of sight field. Okay, that when you look at when you get polarization information, you know something about the line of sight field. And so by comparing those two things, you can get a handle. So in particular, if you measure in all the Stokes parameters, if you're able to have a good enough data to do that, you can infer something about both the field strength and its morphology. So there's some really interesting results coming out of that. So those are the techniques. So, I mean, as we go forward, there'll be new techniques. And you learn new things. I threw this in just because I thought it was really cool. It's not something in wide use or anything today. But again, thinking about information about position on the sky, you can, this is an example of somebody using transiting exoplanets in a particular misaligned system as a kind of probe of stellar surfaces. So you look at the change in the light curve as this over the course of many transits, and that can give you information in particular, in principle, I should say, on the brightness of the stellar surface as a function of latitude. So there's all sorts of cool stuff being done, and interferometry is another example of this. In most cases, though, what we have to do, in many cases, I should say, we still rely on different proxies for these things. So in particular for magnetic fields, we might often not be able, because you can measure, because the fields have to be so strong for you to measure them by direct measurement typically, and we often rely on proxies to get at the whether a thing is magnetically active or not. And so one of those proxies is just the heating of the upper atmosphere, the chromosphere or corona of the star. Just by eye, this is just a map of high energy emission in the sun and a magnetogram. By eye, you can see these things are linked. You don't have to have a complete theory of coronal heating or anything like that to be able to make that link just qualitatively. The physical picture here is that fields, magnetic fields, are linked in some way to the heating of that atmosphere. You can quantify that if you like by looking, again, just looking at the sun directly and trying to link local values of the X-ray luminosity. This is Lx, 20 CGS units as a function of magnetic flux at different locations. So there is this link between heating and magnetic field strength. And if you go out and use that, so we can use that and try to measure magnetic activity in lots and lots of stars. So again, we're trying to understand, the sun is great, but we would like to see how activity and rotation and convection and things depend on parameters like rotation rate or luminosity. And we can't do that with just the one star. So we go look at other stars. And the first thing you find is that, roughly speaking, you tend to find that magnetic activity is common where you have surface convection in a star, and it's pretty rare otherwise. So just to remind you, the sun has a convective envelope, occupies about the other 30% of the star. As you go to lower mass stars, well, let's go to upper mass stars first. You go to higher mass stars, the convective envelope shrinks and eventually basically disappears, although there's usually a very thin convection zone. But there's a convective core that develops. And if you go to lower mass stars, so lower mass than the sun, the convective envelope deepens. And eventually, by the time you get down to about a third of a solar mass, the star is convective everywhere in its interior. So that's the basic story. And you tend to find that, again, magnetism is common in those stars that have surface convection zone, and it's pretty rare otherwise. So if you go up to that upper mass end, there are not that many, magnetic activity is nowhere near as prevalent. There are some exceptions to this, these so-called magnetic AP or BP stars, which I'm happy to talk about if you like, but they're the exception rather than the rule. And you can, so then you know that lots of stars are magnetic. Yeah, that magnetic activity, just observationally seems to be linked to convection in some way. I should say, before we move on, that doesn't necessarily tell you that convection by itself drives the magnetism. It could be an indirect thing, like convection drives differential rotation, which is important for magnetism in some way. So that's something you got to keep in mind. But anyway, so observationally, we see there's some link between convection and magnetism. And another big clue, maybe the most interesting clue in one of the most interesting findings, I would say, to do with stellar rotation and magnetism is this so-called rotation activity correlation. We find that these observational tracers of magnetic activity are linked to the rotation of the star. So this is a plot, again, of the X-ray luminosity normalized to the bolometric luminosity of the star as a function of a measure of the rotation rate. So looking ahead a little bit to what we talk about in the next bits, this is effectively a crude estimate of the Rossby number, so the ratio of the convective overturning time to the rotation period. So more rapid rotation is to the left on this diagram. So as you go to more and more rapid rotation, you tend to find more and more activity in some measure up to a sort of plateau. So beyond a certain point, the magnetic activity stops increasing, and then there's some funny business at the end. Maybe it declines a little bit, but that depends on which tracer you're looking at. So that's really interesting. Just observationally, nothing to do with theory. Observationally, that's an interesting clue that tells you that rotation probably has something to do with either the building of fields or their appearance at the surface or the strengths they get to or something. You see that, by the way, in different tracers of the field too. The thing I've showed you in there is just coronal emission. But if you look at spectropolarimetric results, they tend to at least find the rising part of the rotation activity relation too. This is a measurement on the top panel of the so-called poloidal field squared, and another measurement of the toroidal field. Don't worry too much about that. But again, just as this idea that there is something that that the magnetic fields seem to know about rotation in some way. If you go and monitor these kinds of things for decades, or years at least at a time, you tend to find that some exhibit long cycles and some don't. And that, again, is a puzzle. So the most famous example, this most famous data set on this comes from the so-called Mount Wilson Observatory HK project, which looked at a number of looked at the chromospheric activity of a number of stars over many years. This is just an example down at the bottom of chromospheric, a particular measurement of the chromospheric activity oscillating over the course of years. The way I've clipped it, you can't actually see the time axis, but trust me, it's years. And there's been a lot of debate and interest and an ongoing puzzle, I would say, to do with how that cycle period is related to the rotation period of the star. A little bit of controversy about this, and I'm not going to go into it too much. You can see some of the references down here if you like. But broadly speaking, there seems to be a couple of different branches of activity. If you plot the cycle period as measured in these objects as a function of rotation period, certainly for the less active stars, there seems to be a link between the rotation period and the cycle period. That link I think is much less clear as you go to very short rotation periods. There's been a lot of discussion about where that comes from and different models for that and so forth. So another set of kind of motivations comes from the fact that, look, the sun is losing mass all the time. In the case of a star like the sun, it's not losing a lot of mass. The mass loss rate in the sun is something like 10 to the minus 14 solar masses a year. So that is of the same order, and in fact, about a factor of 2 less than the mass it's losing just by radiation, the L over C squared, if you like. And so the sun's losing all this mass all the time. And the reason that you don't have to go out and check a space weather forecast in the morning or something like that. Earth, of course, has its own magnetic field, which largely protects us from the solar wind that's pouring out all the time. But occasionally, and I mention this mostly for just, again, motivation purposes, if you like. If you speak to different audiences, some people are really motivated by the connection that magnetic activity has on our own society. And this is one example of that. So if there's a big geomagnetic storm, it can knock out satellite communications, it can disrupt power grids, things like this. There's a famous example in the late 1980s where ground currents associated with a geomagnetic storm led to several million people losing power. Lots of examples of satellite damages, changes in the flight patterns you're allowed to take, and all the rest of it. By some estimates, a really big solar storm would lead to something like $1 trillion in damage. So that's not so good. Anyway, there's a lot of interest because of that in trying to forecast solar activity, at least in the short term, and trying to understand where it comes from and whether we're at risk of really big events, as have happened in the past. One famous example of that is what's called the Carrington event. So a very large geomagnetic storm in the 1800s, observed by Richard Carrington. And there's some fun examples of this. I'm not going to go into it in detail, but if you look at this Green et al. 2006 paper, it's got a nice compilation of some of the reports, contemporaneous reports of the phenomena associated with that storm. So in particular, people could see aurora as far south as basically the equator. There's these accounts of the wires of electric telegraphs, the telegraph paper bursting into flames because of the currents associated with this stuff. Anyway, neat stuff. And on a slightly grander scale, it may be that link between the outpouring of matter from a star like the sun and the interaction or not with a magnetic field may be part of what leads to some planets losing atmospheres and others not. So there's some neat stuff, neat puzzles, I should say, associated with this coming out of the MAVEN mission that started to measure. So Mars has a very, very tenuous atmosphere today. It also has no global scale magnetic field anymore, although we think it did at some point in the past. It has a remnant crustal magnetization. Anyway, so it doesn't have that sort of protective shield that we do. And MAVEN did some measurements of atmospheric loss during a particular geomagnetic event, which is kind of cool. Anyway, I'll leave you to explore that on your own. Right. So as this solar wind comes out, it's carrying away mass, but it's also carrying away angular momentum. And so the stars spin down over time. And so far I've kind of portrayed magnetic fields as the passive agent, if you like, that star. The more rapid the star rotates, the more magnetic field it has, let's say. But I mean, the magnetic field can drive behavior too. So it's probably involved in what's launching the wind, but it's also involved in the angular momentum loss rate. So the magnetic field largely sets the lever arm for the wind. And so if you change that lever arm, for example, by changing the field strength or by changing its morphology, so you change it from a dipole field down to a quadrupolar or octupolar field, which has a smaller lever arm for the same field strength, you'll change the spin down rate. So this plot on the left is a famous plot from Andy Szymanich, 1972, looking at essentially the fact that stars spin down over time. If you look at their rotation rate and also their tracers of chromospheric emission, they tend to follow this so-called t to the minus a half law. And that, again, that spin down, the rate at which they spin down depends both on the mass loss rate and on the morphology of the field, and on how well those two things are coupled. So there's a whole industry that tries to understand this. You see that spin down, that spin down dependence, if you like, if you go looking at rotation data for stars of different ages and masses and all the rest of it. So if you look at young clusters, for example, as a function of stellar mass, you see a whole mess of rotation periods, some very fast, some very slow. As you look at older times, there is much less spread. Okay, so the stars sort of converge to some sequence that, and then follow this so-called Szymanich style t to the minus a half spin down over time. So there's, again, just an interesting observational puzzle associated with how you do that. There's a whole industry in trying to understand how the stellar, how the spin down is affected by things like magnetic field strength, by rotation rate, and all the rest of it. These are some examples from a nice paper by a colleague of mine at Exeter, Sean Matt, 2015, that looked at, basically you populate a synthetic cluster. These are simulated cluster stars. They start out with some, at a very young age, 5 megayears, with a spread of rotation periods, and you have some prescription for how their spin changes over time, which is physically motivated or motivated by simulations or whatever, and you ask how they would evolve. And again, see the paper if you're interested in all the details, but roughly speaking, they first move to shorter rotation periods, and then in a mass-dependent way, they lock onto this kind of Szymanich style spin down. But the spin down time changes as a function of mass, and there's a lot of interesting questions associated with how fast stars spin down. And that, you now know that, courtesy of the slide 5 minutes ago, you know that magnetic activity is linked to rotation rate. Okay, so if the spin down has changed, that tells you that the magnetic activity is also going to change. So in other words, it tells you, this is way back at the beginning of the talk, I showed you this plot of the fraction of stars that are active in a particular tracer of magnetic activity as a function of spectral type. And that's a link to this spin down stuff, right? So the stars at slightly higher masses spin down faster, they lose, which means they lose activity faster. Their activity age, people like to talk about, is short. There's all sorts of interesting puzzles there, but also some interesting data. I mean, the idea is that if you had enough data on this stuff, you could infer all sorts of interesting things about how fields are evolving over time, how mass loss rates are evolving over time, and so forth. And I would say that, broadly speaking, the data is pretty good at this point. Okay. Now, in the last, I think I've got about 10, 15 minutes or so like that. So in the last few minutes, I wanted to talk a little bit about this is all fairly detailed stuff, okay? If I were a stellar astronomer or somebody coming into astronomy for the first time, and I wanted might like to know what effects, if any, this stuff has on stellar evolution or stellar structure. So what effects the rotation or magnetism or the details of convective transport have on those things? And look, the zeroth order answer is not much. I mean, this is, just being honest, this is an example of what's called a color magnitude diagram, a version of an HR diagram. So the brightness of the thing is on the vertical axis and the color is on the right. Just overlaying data from a particular cluster that is a collection of stars with about the same age on a theoretical isochrone from some models, standard 1D stellar structure models by Isabelle Baraf. These models aren't anything fancy. I mean, they're quite fancy in some ways, but they don't have exotic things like rotation or magnetism or non-standard mixing. They're just, pretty bog standard 1D stellar models with good atmosphere models and things, the rest of it. And they, yeah, I would say they do pretty well, right? So you can view this as depressing. I mean, if your goal was to prove that everybody in the universe ought to care about the details of stellar rotation and magnetism, and that the data doesn't support that. So order of magnitude, the gross structure of a star, is set by other physics, and which we'll talk about in just a second. And I guess the point I want to impart to you, which I probably don't need to tell you, but I will anyway, that right now we're awash in data. Okay? There's an enormous amount of new and very powerful observational constraints on stars coming out all the time. This neat little movie is from the Gaia collaboration. Gaia Data Release 2 released position and brightness for over 1 billion stars, and lots of other information, parallax, proper motion, and color for, again, over 1 billion. This visualization is just how you might create something like an HR diagram by slicing that data and compressing it. Anyway, the point is just that we can do a whole heck of a lot better than order of magnitude studies of stars nowadays. And so as you get more and more precision along those different axes, information in time, information in wavelength space, information in position on the sky, parallax, for example, or proper motion, you learn more and more things. And so as we've started to do that, there are new puzzles that have started to emerge. So one example of that, we'll get back to the evolution stuff in just a second, but I mean, lots of people have started to look in the last decade or so at impacts of stellar evolution, impacts on stellar evolution and stellar structure of things like rotation, magnetism, anomalous mixing, stuff like that. So this upper plot is just showing you a couple of examples of stellar evolution tracks with a particular prescription, which may or may not be right, but trying to incorporate the effects of different rotation rates, showing that they do behave slightly differently at sufficient precision. There's at more massive stars, what outcome you get as the final stage of stellar evolution, whether you get a magnetar or not, seems to depend to some extent on the angular momentum transport in the progenitor object. So that's another area of great interest at the moment. And I think some of the most interesting things, which we'll probably hear about quite a bit more later in the week, have to do with constraints from astroseismology. So one of the most striking things is that if you go and measure the core rotation rates of evolved stars, so red giants, for example, you tend to find that they do not match simple prescriptions, that is, with standard amounts of angular momentum transport, very well. And in particular, there needs to be quite a bit more angular momentum coupling between the core and the envelope than you might naively have predicted. And so there's a lot of discussion about where that additional transport is coming from. There's a nice paper here on the bottom by Matteo Cantiello from a few years ago, looking at different models for what might be providing that angular momentum coupling. So looking at, in particular, something called a Taylor-Sprout dynamo, that is a magnetic field generation scheme operating in the radiative stably stratified zone, but also looking at things like meridional circulation and comparing them to observations. There's a whole set of interesting puzzles here you'd like to understand, which is helping nowadays, I would say, to motivate us to look into how strong the fields get as a function of rotation rate and things like that, and how they transport heat and how they transport angular momentum. And then, going back to stellar evolution for a second, one topic that I've become interested in myself over the last few years has had to do with these claims that at a detailed level, again, if you're not looking at order of magnitude change, you're looking at the 5 or 10% level, some low mass stars seem to be bigger than models would predict they should be. So if you look at so-called eclipsing binary measurements of stellar radii, this is one example, comparing the radii as a function of mass in a collection of targets for which you have very, very precise radii, right? These eclipsing binaries, you can get strong constraints on both the radius and the mass. So you know the radii quite well, and they're discrepant by something like 3 to 15% from what the models would tell you they ought to be. Now, that may not sound like much, but changing a star's radius by 5% is actually really tough. We'll talk about why in a second. And And that also means that if you're looking at a young star, so 5 or 10% in radius might not seem like much, but that ends up being about a factor of 2. Stars, as they're on the pre-main sequence, they contract. Their radius is changing over time. So if you get the radius wrong, you get the age wrong. And in some cases, you might be getting the age wrong by a factor of 2 or something like that. So a lot of people have suggested that maybe one of the things that's going on is that our model of how convective heat transport works is wrong, so that perhaps the convection is less efficient than it would be in the absence, that maybe rotation or magnetism are inhibiting the convection somehow. And we know that's not a crazy thing to think about, right? Because magnetism, we know, inhibits convection in extreme cases. You look at a sunspot, right? And the reason the thing is dark is because the magnetic field is locally inhibiting convective heat transport. It's dark because, there's less, it's cooler, et cetera, et cetera. So we know that can happen, at least in some regimes. So the question is, can it happen on some kind of global scale? And I'm mentioning this problem not because we're going to solve it today, but because I want to use it as a little bit of a motivation for all the stuff that we're going to do. We'll do a little bit today, but then more in the next 2 lectures. If you wanted to study this quantitatively, if you wanted to understand whether it's possible for rotation or magnetism to do that, you need to know a couple of things. One is you need to know roughly what what size of effects you can expect from the magnetic field. So to do that, you need to know how strong the fields are. And I've listed a few example fields here. Sunspots, maybe a kilogauss, 1.5 kilogauss, a bit stronger if you like, but to order of magnitude, it's a kilogauss. That's not that strong, really. I mean, a good kitchen magnet can be 10 to 100 gauss, but the sunspot's a very large kitchen magnet. It's very big. The Earth's, the global scale field on the Earth is of order of Gauss. And the magnetic pressure, we'll talk about this next time more, but roughly speaking, the magnetic pressure scale is like the field squared in CGS units. So the dynamical pressure in CGS units associated with a field of a kilogauss is of order of 10 to the 6 dynes per square centimeter. So to understand whether that's likely to have an effect, you'd need to understand something about the conditions that prevail in a star. So I want to talk for just a couple minutes, again, aiming this mostly at those of you who've come from a more fluids background or a plasma background but haven't studied stars before. I just want to give you a sense of what a star is like as a physical object, and why they're not that sensitive, why models that involve no rotation and no magnetism can do okay. What hope do we have? So the basic story is that stars, you can get an awful lot of information on stars just from the fact that they are bound objects. They're in hydrostatic equilibrium, and they're in roughly thermal equilibrium. And from that basic, and then the other piece of it is that, at least at the surface, the transport is by photons. And so just those two things together tell you an awful lot. Now, I'm not going to do a lot of examples of this, but I wanted to go through one maybe in detail. So let's imagine that we have an object that's in hydrostatic equilibrium. So dPdr, the pressure gradient, is of order of -g rho at every point in the star. You'd use that to estimate the central pressure in the star, again, just to order of magnitude, by saying, well, approximate the gradient as 1 over r. So central pressure over r is of order g, which we'll say is of order gm over r squared, times the mean density, m over r cubed. And that'll tell us that the central pressure, just plunging those things together, has got to be of order gm squared over r to the 4th. You could do that also just dimensionally. So you could already, at this stage, take that and you plug in your favorite values for the mass and radius of a star and get an estimate. And this is something I encourage you to do after the lecture, if you haven't done this kind of thing before. Just try to estimate what the central pressure in the sun is, or in Jupiter for that matter, if you like. And you can compare that, if you like, to the dynamical pressures associated with the magnetic field. And the conclusion you probably will find is that it takes a heck of a strong magnetic field to be comparable to the gas pressure, right? So if you wanted to change the structure in that way, it's tough. You need 100 megagauss fields or something like that, which are not plausible, not very plausible, I should say, on other grounds. But let's think a little bit more about it. So we're looking for smaller effects. So you're not just globally plonking such a strong field that you make the star puff up or something. Let's look at something else. So if you ask what the specific entropy is, so the entropy per unit mass as a function of position in the star, let's say, at any given spot, it's related to the pressure and the gas density. So it goes times a constant and up to an arbitrary constant. It goes like the log of p over rho to the gamma. So just putting in those kind of homology relations from above, at the center of the star, for example, it'll be of order log g m squared over r to the fourth times r cubed over m. And for a gamma equals 5, let's say that gamma is 5/3, so an ideal gas. Right, and so plugging through and kind of canceling things out, you'll find that it goes like this, that it goes like the log of g times r times m to the 1/3. So what that tells us is that at fixed mass, the radius of a star is proportional to e to the specific entropy. In other words, that the entropy, if you want to change the radius, you pretty much, one way to do that is to change the entropy. And the two, in fact, are very, very tightly linked. So you can see this. There's other ways of getting at this. If you constructed a polytropic model, for example, the entropy comes out directly as part of that. But anyway, the radius is a function of the entropy. If you change the entropy a bit, you can change the radius. But changing the entropy is very hard. So that's what I mean when I say that to change the radius by 5 or 10% is actually no easy feat. The easiest way to do it would be, because the entropy is a thermal quantity, the easiest way to do it would be to change the thermal, to add a thermally relevant field. But that is enormous. That is, again, is enormous. So that's a 10 megagauss field or 100 megagauss field, something like that. So that's very hard to do. Another thing you might look at is just, it turns out, and again, we'll get to this a little bit later, that one of the things convection tends to do is isotropize entropy in the interior. So this panel on the top left is showing just some pretty bog standard 1D stellar models of fully convective stars. These were done by Lewis Ireland, a former student of mine a couple of years ago. Fully convective stars as a function of radius. The horizontal axis is density, but you get the idea. It's dense in the center. To the left, it's less dense in the atmosphere, right? So throughout most of the interior, for a reasonable convective prescription, the interior is pretty close to isoentropic, right? So the thing sits on an adiabat. But which adiabat you're on depends on the convective model that you use. So, for example, in standard mixing link theory, the way that you change convective efficiency, if you like, is by changing alpha, this mixing length parameter. And so changing alpha changes which adiabat you're on. If you make it a lower alpha, you end up with a larger, less efficient convection, a larger delta S to carry the same flux, and you end up on a higher adiabat and thus a larger radius. This plot in the bottom right is just showing that if you take two models and you monkey around with the alphas effectively, or change the convective efficiency in other ways, you change the adiabat, and that directly changes the stellar radius. So you can get to these inflations of 10 or 15% by monkeying around with the adiabat. This is just playing around though, right? What you'd like to do is to actually have a theoretical, a model of how convection and magnetism and rotation conspire to build an entropy gradient. So here we just dialed it in effectively by changing alpha, maybe even as a function of depth in some cases if you want to be a little fancier about it. But that's just a simple prescription. Right now, there is no universally agreed prescription for how you ought to incorporate the effects of magnetic fields or rotation into a 1D stellar model. So we don't have a good handle on what effects these things have, how strong fields have to be before they could have an effect on the rotation, on the overall structure of the star, and so forth. There are lots of attempts out there. I've just shown one example of that. So, some models from Greg Feiden. He's done some really interesting work trying to construct so-called magnetic models, where you put a physically plausible model for how the entropy gradient, the convective efficiency, is changed by the presence of a magnetic field. And those magnetic models seem to match the data quite a bit better than so-called non-magnetic models, if you like. But it's still, I would say, fundamentally a little unsatisfying because we don't have a first principles model of how you get to that entropy gradient. And so one of the things I'm going to be talking about over the next couple of lectures is just how you try to build those models. So we've talked a little bit today about the observations that motivate this stuff. We've talked a little bit about the conditions that prevail in stars, but the end of the day, Again, to zeroth order, the gross stellar structure doesn't know that much about rotation and magnetism. But we now have this enormous trove of data that can do a lot better than order of magnitude. So if you start trying to do stellar astronomy at the 5% level or 10% level, there are all these interesting questions that open up to you. But to answer them, you have to have quite a detailed understanding of what kinds of fields you build, how those depend on rotation rate, and how they feed back on heat transport and on angular momentum transport. So you need, in other words, a quantitative understanding of how strong the fields are and what they can do. So that's what we're going to be trying to build over the course of the next couple lectures. I'll stop there. Thanks for your time.